No, I left that current folder yesterday. And sometimes it gets digging, you know what I mean? I'm hunting it down all day.
Yeah, exactly. Yeah, no, I don't think I know, sort of what we call that.
It's captured. Okay, everybody, let's go ahead and get started. Thanks, everybody, for coming today. And I'm happy to introduce today's speaker, Dr. Joel Fodrie. Joel is a professor at the Institute of Marine Science at the University of North Carolina Marine Lab there at Morehead City. And he's been there since 2009. Before that, many of you know, Joel was here at the lab for 3 years. And he came here immediately following his PhD work at Scripps and did postdoc work here with Sean Powers and me, then went on to be a research assistant professor here for a year before North Carolina stole him from us. So Joel's come back. We actually still have some data that we're working on from those early days. In the interim, Joel has really carried out a lot of work since he's been at North Carolina. He's going to talk to us about some of that today. But I wanted to point out that Joel is a fisheries oceanographer and a marine ecologist, and his interests are really broad. I know some of you already know him and have worked with Joel, but he's been interested in connectivity between inshore and offshore fish habitats, and he's looked at otolith microchemistry to sort of trace some of this. He's also worked with habitat restoration, shellfish habitat restoration, and lots of different things. So he's broadly based. He's published an awful lot, some 30 to 40 papers. So Joel has a work ethic that we could all imitate and feel good about. So I'm really happy that he's here. He's going to talk to us about some of the things he's been doing since he left the lab. So Joel, take it away.
Thank you. So it's neat to be back, of course, and so I hope you're impressed, because I don't want to leave a bad impression. And I kind of want to do three things today. Number one is, we do get to work in these neat systems, and at the very least, I hope you leave saying, gosh, these coastal systems are neat and they're dynamic, and we can have a lot of fun and learn a lot, and then sort of give back and hopefully inform better management. So I do want that to happen. The other thing I want to do is regarding this term landscape. So I remember having a conversation with Dr. Heck one time about landscape, and he said, well, what does that mean? Landscape, that's just like a vague term. And I was like, God, dog, he's right. I don't know what landscape really means. And for every different critter, landscape may mean something different. And so some of this talk is about me trying to pursue that interest in trying to figure out what landscape means and actually use it in a way that's real and has some value. And you can judge, whether or not that happens. And then the last thing is I really sort of believe in the ecology of place. And so I don't presume that the things I'll talk about in North Carolina apply perfectly here. Some of these principles that we think we're seeing in our system may be very different than what you have here, and that'd be something cool to talk about if I happen to see you in the hall or a meeting later. And so, be critical in the sense of, well, okay, you're saying that's the way reefs are regulated, but that's a bunch of malarkey in the Gulf of Mexico. So anyway, we'll try to attack those three things. I just had to start with acknowledging a lot of people, students, technicians, collaborators, different places. Sean Powers, we use some of his instrumentation, so we've benefited from a lot of help. And we've had a good record of funding that allows some of this to happen, especially the restoration work. It's pretty large scale. I'm sure y'all are very familiar with that type of scale because I know the work that's done here. It's not always cheap. So the things I wanted to do today, and we may not get through it all, and that's okay. Just first wanted to give you sort of my broad view of habitat and service linkages, what we know and what we don't know about that in a quantitative sense. And then try to build on what we know, go through these few examples. The first two are sort of grouped together because it's about habitat use by fishes and patch size and orientation within a landscape, as I like to use that term. And then move on to some oyster reef work, first talking about how landscape affects the development of reefs over fairly small scales. And then also how that development across landscapes ultimately impacts the service delivery of those oyster reefs. And it's just really, really variable and dynamic in space. And I kind of want to get through enough to leave you with that sense of that reality. All right, so I don't want to belabor this point long, but estuaries are made up of marshes and oyster reefs and mudflats and seagrasses that are just terribly, terribly valuable in terms of the services they provide: water filtration, habitat provision, recreation, tourism. Like, nobody would deny that. Like, everybody, yeah, I get it. Like, sign me up for that. But what our lab has become interested in is, well, how do those services scale with habitat availability or orientation? And in the terms of like fishery production, as one example, we've lost a lot of these habitats. And I'll defy anybody to tell me what that's really meant for fisheries. So in North Carolina, we've lost, some estimates are 99% of our oyster reefs. We've lost 99% of oyster reefs. Oyster reefs are an essential fish habitat, and I can't tell you what that's done to fisheries at all. And I don't think anybody can. I don't know if there's one less red drum or a million less red drum or speckled trout, and no one does. And so while we all have this sort of loose appreciation for, yes, habitat's critical, like, we don't have very good quantitative links between habitat size or orientation and that production of services. People have measurements of nitrogen cycling within oyster reefs or marshes, but yet we don't know if you project back up and have a lot more oyster reef, is the marginal value of service linear as you increase habitat, or does it asymptote, or does it somehow increase exponentially with habitat availability? And that fundamentally limits what we can promise people about, well, let's get back to pristine, and then you'll get this or that. I just don't think we know that well. And so one of the ways I'll try to attack, that uncertainty is to think about this issue of landscape. And I do think our estuarine systems are a useful place to at least consider that idea. Landscape is about habitat heterogeneity and connectivity over scales that can really affect ecological pattern or process. And process in this sense might mean service delivery. And marine systems have patchiness to the scale of this room. You can easily move from seagrass to mudflat to marsh over a fairly small scale. And in terrestrial systems, it's typically a much larger scale. If you're in a forest, you're in a forest for a ways. If you're in a seagrass meadow, you may only be 10 or 15 yards from a very different type of habitat. And so, here's a picture from North Carolina looking down on the landscape with oyster reefs on a sand flat, but also oyster reefs up against a marsh, seagrass that's either contiguous or more patchy in places, over sort of 2 or 3 football fields. And so there's a ton of heterogeneity, all sorts of habitats, and we don't know how connected they are or how their connectedness affects their function or the service delivery. And so I like to talk about that because it's fun, and I also think it has some applied value. And I think this idea of landscape is also very relevant for this idea of place-based ecology. So, it's no secret that right now we're concerned about climate change over really broad scales, and it's in the media a lot. But I sometimes wonder if, things that happen at much smaller scales, like putting up a seawall or dredging a channel, if that actually has sort of more aggregate effect than something that's broad scale like climate change. Because about 15% of our shoreline is hardened nationally. No matter where you go, on average, 15% is hardened, and that's a lot. And that's a scale at which trophic flows or movement is going to take place, and we've really altered that. And so I think landscape and sort of place-based understanding they sort of go hand in hand. All right, so the first 2 studies I'm going to talk about deal with habitat patches and how fish use them. And they're sort of very, academic, sort of, hypothesis-driven questions, but I do think they inform us about this real-world issue of scaling services. And sort of to reiterate what I said before, in a general rule, we certainly think that, if you can increase habitat area, and this is sort of marsh area in Louisiana, you should increase fish reproduction. And these are actually shrimp data back in the day. And this satisfies, I think, most all of our intuition. Yeah, more habitat, more production. But in my mind, these data are actually shockingly quite rare. These data are not something you find every day. And to make this point, I've asked around, and the point I make is going to be, I think, true, whether or not the exact details are right. But habitats like marshes and oyster reefs, they're considered essential fish habitat. And, we have all these stock assessments for different species. Hundreds of different species have stock assessments. Like, for how many of those species is habitat a term? Or is habitat, like, explicitly considered in how healthy or how productive a stock is? Is it half? Is it 2/3? And it's not. It's like 0. Or maybe it's like 1%. I asked one fisheries guy who's well informed, and for the couple hundred of stock assessments that he knows about, like 3, have a habitat term, and it's for something that's very stationary, like a scallop that doesn't move, right? And so you start talking about fishes that move and are basically invisible to us, it gets a lot harder really fast. And there's been other works about this question. Well, why is it so hard to fish ecology to habitat? This is the title of just one paper that was published about a decade ago. And, I think there's lots of reasons that's true. You can certainly go to a habitat on any given day, like this mangrove stand, and you could go back to that same site or a site that looks to your eye the same, and there might be no fish, right? And so, these fish are very patchy, and they're moving, and they're cueing accurately yet or understand in a very sort of multi-dimensional niche space. And so these are just some of the things that occur to me about why it's hard to make those links. And number one is, maybe not all seagrass is created equal, and we should think more about, the differences within seagrass beds and how fishes perceive that. And then the fishes also, they don't read the textbooks, so they don't know that they're supposed to do a certain thing because that's the way we understand their life history to be. And we've looked at how much individuality there is among fishes, and that's an emerging literature in terms of specialization broadly. Diets or habitat use or reproductive behaviors. Fish are really quite like us in the sense they have sort of personalities. You'll see some like to travel a lot and some don't like to move hardly at all, even within a population. So this one, is just sort of my default, why we have a job is because, if we were studying forest, if you want to know how a tree's doing, you put a tag on it and you come back the next day. If a tree's not there, it's probably dead. But a fish, you don't know that. You don't know that it's dead. And you certainly don't know if it's been eating well or if it's grown a lot or very little. So just being able to follow fish through space and time is hard. And so some of the tools we use is just to get around that very basic thing, which then impacts a lot of what we understand about multiple aspects of fish ecology. And then this last one is what I talked about before about sort of scaling up. So, we do our experiments a lot of times on fairly small scales, maybe in cages or in tanks. And we can tell you the structure is valuable or that they feed better or avoid predators better in a tank or in a cage or at some small scale. But how does that dynamic change if you go up to football field scales? That's non-trivial, and that's hard to do. And so for our restoration work, this is fairly important because we want to be able to promise people you'll get more fish if we do this, and we don't know that. Okay, so the first experiment I'm going to talk to you about is about this issue of fragmentation, and it's really been led by a postdoc named Lauren Yeager in our lab. And I think there's nothing secret here about fragmentation. A lot of things we do in developing coastlines takes these big contiguous patches of habitat, might be seagrass, in our case it's seagrass, and it sort of diminishes the amount of habitat, it creates more patches, it changes the distances between patches as you fragment, it changes the edge to area ratio of the landscape. A lot's going on, right? And we do know that, as you sort of talk about fragmentation broadly and you're losing habitat, you tend to see fewer individuals in a less diverse community. But is that specifically just the area function, or is that something else about fragmenting these landscapes that's driving that pattern? And we're lucky in North Carolina in that we have all sorts of landscapes of seagrass. So here's just one aerial image. This is about 500 meters. And you can see these big contiguous patches here and here and here and here. And then you can see these really fragmented seagrass landscapes too that aren't that far apart. And there are some environmental differences that we know. But we have this wide range of orientations of the way seagrass is structured in our system. And what Lauren wanted to look at in particular was this idea of fragmentation per se, which has been studied here and other places, but at a bigger scale. Is what I would say. One of the things she did that was kind of neat is she worked at really big scales. So fragmentation by itself, is not habitat loss. Fragmentation per se can occur without habitat loss. And she really wanted to look mechanistically, well, what drives community patterns? Is it the habitat loss or is it fragmentation per se? And so her design was to find patches of different sizes that were either continuous or were fragmented. So she had some patches that were, 80% seagrass cover. But that might be orientated either as one big patch or as several patches. And so she matched those up from really high cover all the way down to low cover in pretty big areas. I don't know if I have a slide. Yeah, I do have a slide. So these are 16,000 meters squared boxes, right? So these are big areas in the landscape. And she was lucky that the state had just flown the coast, and she had really good aerial imagery to map the seagrass and look at the quantitative metrics for fragmentation and rank patches as either contiguous or fragmented. And so after we mapped it, we went out twice and we sampled it with nets and trawls and little push nets and cores to try to look at the different parts of the community. And all I'm going to show you is the fish data. But what Lauren really wanted to test was this conceptual model that had been proposed by Fodrie, this habitat amount hypothesis. And based upon loose data sets and kind of her own intuition, what this person had proposed is that if you want to look at the effects of fragmentation, shown in the blue and the red, separate from habitat cover, what she proposed is that the effects on species diversity, at least, might be described by some thresholds. So if you have a lot of habitat cover, you can fragment it, and really you're not going to see a functional change. So fragmentation by itself has no impact. But in her model, there was probably some threshold below which, if you kept fragmenting the landscape, even if you didn't change the amount of habitat, you were going to see a change in the community. And Lauren wanted to test this concept. And so I'm just going to show you data from the trawls. And Lauren went out and she towed a net and she looked at what she caught. And so what you're seeing here is you're seeing species richness across different levels of seagrass cover. So this is almost, a 16,000 meter squared seagrass bed. Up here at the high end, all the way down, either continuous bed or fragmented beds. And lo and behold, she empirically basically shows that this conceptual model has maybe some validity to it. So anything above like 30% cover, you get the same number of species in a fragmented bed that you do in a continuous bed. But when you get below that, you can actually get to the point where you've got about half the species in one of these fragmented beds relative to a contiguous bed, even if the amount of cover, the overall habitat area, is the same in our box. So I won't go into a lot of detail, but we've done some follow experiments to mechanistically try to understand, well, what's happening here. And if I just group the landscapes into four types, either continuous beds that have really high cover, continuous beds that have really low cover, or these fragmented beds that have high or low cover, what you see is that for those first three landscapes, you basically have a certain assemblage of fishes. A lot of you probably recognize these fishes as pinfish and spot and filefish and flounders. And it's just in this one type of landscape, the fragmented low cover, that you start to have species drop out. And the species tend to be these filefishes and the pipefishes and toadfishes and pufferfish. And these are the cryptic things. These are the things that they don't move around a lot. They're not conspicuous, shiny fish that are kind of schooling and moving around. These are things that like to hide. And there's some other mechanisms, but one mechanism that's interesting is that, these are fishes that have a hard time making that jump between patches. And we've done some experiments to look at that. And so if for some reason they get knocked out of a patch, they have a really hard time recolonizing that patch. And therefore, we think that's one of the reasons that we see lower species richness in these low-cover fragmented beds. Okay, so moving away from that, I'm going to talk about an experiment that one of our graduate students has been running. And this is asking questions about that scaling issue. So, if we could get outside the meter squared scale and go up to much larger scales of habitat cover, what are we going to get in terms of fish production? Or is it a one-to-one relationship? So the question is, if we increase habitat availability, do we see sort of overall production of a system go up and up and up and up and up? or does it begin to asymptote at some point? Because fishes, they don't sort of benefit from every unit of habitat addition. These might be something like an edge predator, where if you keep adding habitat, if it's all core habitat, those edge predators, they don't perceive it, right? And so they don't benefit. And this is sort of, not tangentially, it's sort of directly related to this idea of this adding habitat subsidies increase production, or does it just redistribute fishes? And therefore, are you changing the aggregation, patterns of fishes? And so the idea here is, you've got some habitat amount with a certain density of fish, and if you double that habitat amount and you go out and you measure the density of fish, are you going to see that same density and therefore indicating maybe production? Or are you going to see densities go down? Basically, these same 4 fish have just redistributed themselves in a way so that you've not changed the number of fish in the system. You've just redistributed them, okay? And that would relate to that productivity sort of asymptoting, right, with more and more habitat additions. And so we wanted to test this in the field, and this is not a huge scale thing, but conceptually it's going to build, I think, to an experiment we'd like to run at larger and larger scales. And so what we manipulated in the field was habitat availability and the orientation of habitat. So we basically had 2 treatments. We had these solitary habitat patches, which are low habitat availability. And then we had these habitat patches where habitat availability was comparatively high. And what we measured was the density of fishes on this solitary patch or in this central clustered patch, okay? And if the fishes are, soaking up that habitat and benefiting from every marginal increment of habitat addition, what we would expect to see is an equal density of fishes here and here in this patch. But if the fishes are just kind of distributing themselves among all the patches and we're not really increasing the productivity of the system, we'd expect to see comparatively high densities here and much lower densities here, right? Because there's the same number of fish in the system, they're just changing their distribution. So we sampled this for about 4 or 5 months after we set out all these basically cinder blocks. We called them reefs, but they're basically cinder blocks. And you can see a cluster patch here with the sort of focal habitat here in the middle and this ring of habitat subsidies around it. And these are the types of beasts that we were looking at in the system. So, we would get a lot of stone crabs, a lot of toadfish. We also got a ton of sheep's head. We have a ton of black sea bass in our system, sort of the reef-associated fishes. We have other types of swimming crabs. Had a fair number of lane snapper, which are also down here. Had a few lobsters, not very many, but they do show up in some of our systems. We don't know if they survive, but they're there for a while. And then some sort of really cool tropicals that just kind of come up and they're looking for habitat, and it's a hard substrate they don't usually find, and so there they go. They recruit to our stuff. And so what you're going to see now are data through time, shown here, showing the abundance of critters either on that low habitat availability treatment or on that high habitat availability treatment. And the first data are from little itty-bitty small juvenile recruiting stone crabs. And sure enough, it tends to be that they get redistributed when you just add more and more habitat. We don't think we're actually increasing their production, i.e. they're probably not habitat limited at the scales we're working at. So if you add more and more habitat, all you do is drive densities on a per unit basis down and down and down and down and down, okay? So no real change at the population level. For the adult stone crabs, it's quite different. So the more habitat we add, the more critters we can find. Like the raw abundance goes up and up and up because the density is not changing through time, right? And, we set out with a very different question than some papers published by Mike Beck in the 1990s. But he was actually testing this in a different way in the 1990s, and our results in a very different system are really comparable to his for stone crabs. But we also have lots of other critters we were looking at. So let me orientate myself. So this was small fishes, things like blennies and gobies and little juvenile lane snapper and pinfish, lots of fishes that we just kind of lumped together for this plot. And again, like their abundances are staying the same whether we have only a limited amount of habitat or a ton of habitat. So we think we could actually increase the production of the system if we did have more habitat, because density is not going down at the scales we worked at. And then we also looked beyond density, and we actually looked at feeding and trophic transfer. Because on these blocks, we can look, and sheep's head leave a very characteristic scraping pattern when they feed. You see this white scrape, and you know it's a sheep's head feeding bivalve. And as you increase habitat area, that feeding rate doesn't go down. So these sheep's head are not only benefiting from just hanging out and the density staying constant, but their feeding rate doesn't go down. So they're clearly looking for places to feed at the scales we worked at. And then in terms of sheep's head specifically, we did some video captures of these habitats, either the isolated ones or the really abundant habitat ones. And what we see there is actually on the high abundance habitat ones, densities are actually much, much higher, right? And so we've kind of coined this like they're hyper habitat limited. And when you watch the videos, what you see is, they're fairly territorial to some degree, and they chase each other. And so if you've got a habitat that's this size, you're only going to support one fish because it's going to rule the roost, and all the other fish just have to go off somewhere and get scraps. But when you reach a threshold amount of habitat, what happens is the fish just start playing musical chairs, right? And so all the fishes can feed on these blocks. And so the behavioral interactions between the individuals within a population or among species really matter. And it is possible to be like hyper-limited, and you have to cross a threshold before you can get, sort of maximum usage of a habitat, which was pretty neat. All right, so having covered that, I was going to move on to some of the restoration work that we do with oyster reefs. And I may not get through all of this, but I'll try. So the first thing I want to talk about is how landscape actually affects the evolution of our reefs in North Carolina. And so to orientate you, here's Cape Lookout, North Carolina. Our lab is here in Morehead City. This is Beaufort Inlet. This is the Rachel Carson National Estuarine Research Reserve. And a big part of that is Middlemarsh, which has been a wonderful natural laboratory for lots of researchers for a long time. And this is an aerial imagery of a part of Middlemarsh where, again, you've got seagrass and marsh and oyster reefs that are either connected to marshes or not. And one thing we've taken advantage of in this system is that not all these reefs are natural. So a lot of these reefs were restored in the 1990s. And so they are a manipulation in the field that's been going on now for 15 years, 18 years, some of them. So we have an 18-year-old field experiment of how landscape affects the ecology of oyster reefs. And this was work originally started by John Grabowski and work that we collaborate on. And so he certainly deserves a lot of credit for that. But one of the things that John did is he built these reefs either totally away from any other type of structured habitat, or he built them really connected to other types of structured habitat, either seagrass or a marsh. So there's a reef that he built kind of next to a marsh. There's one over here that's next to a marsh. And he designed this to look at, well, how does landscape affect the ecology of these reefs? And he published his results after 3 years of study. And when I got to North Carolina, I said, I don't want to do any oyster work. Like, God, I hate oysters. They're terrible. Like, they cut you and they stink, and just keep me as far away from oyster reefs as I can. But the one thing that I wanted to do was I wanted to revisit his reefs, and I wanted to look at how fishes use his reefs. And that was kind of a gateway drug to like a lot of other oyster work. And they've made me a convert. I'll say that for oyster reefs. They are a neat system to learn about ecology, and funding has been there to do oyster reef work. And so we've done our fair share of oyster reef work in the last 4 or 5 years. But anyway, we revisited his reefs, and we said, well, how are they looking after 15 years, not just 2 or 3 years? And I could show you graphs, but I decided I didn't want to because you don't need graphs. Like, my grandmother can see the differences in these reefs. And so, it's nice when you don't need stats, right? So what I'm going to show you is I'm going to show you 2 reefs here and here. And, on a windy day, I could just about spit from one to the other. I could certainly throw a baseball from one to the other. So they're not very far apart. So this is a reef that was built out on a sand flat. And 14 years after it's constructed, there's about 4,000 oysters per meter squared, okay? And the reef is about that tall. And if you move just like 30 meters to one of those reefs that were built up against a salt marsh, the density is about 100 oysters per meter squared. That's not terrible, but it's not 4,000. And it hasn't really grown at all since it was built. It's at the same elevation it's at the same relief as when it was constructed. And this is all, natural patterns of settlement and growth and survivorship. And some of you are probably already thinking, okay, well, what drives this? And we thought some things, and we've had a student do some experiments to look at different mechanisms that may drive this. And one we thought about was, okay, well, maybe flow is reduced here, and so you're not having the same food delivery or the same larval delivery, and therefore the reefs don't look as good. And our data say that's not what it is. Like, you get the same number of larvae settling here, and the flow rates aren't that different, as it turns out. And another thing we thought about was, okay, well, what about some sort of top-down force? So maybe this marsh is a reservoir of little nibblers that love to come out and gobble up every little spat that settles. And yeah, like the experiments we run little, oysters on little plates, like little poo-poo platters, and the little nibblers come out and they just chomp them when they're on this reef, but not on the reef that's just 30 meters away. And so, everything else being equal, just that connectivity with a marsh really fundamentally affects how these reefs can evolve over scales from me to that map. And that seems non-trivial in terms of, doing restoration work. So one of the main clever things that we did is when we first started looking at these reefs, we also noticed that even though all these mudflat reefs look good, they don't all look the same. And it was like, well, why are all these mudflat reefs, a little bit different? Like, we couldn't quite figure it out. But the first thing we need to do is we need to measure them. Like, okay, well, actually, let's get some measurements of how they are similar or different. And we have a really good sedimentary geologist in our lab who was doing work with beach erosion and marsh erosion. And he had this system, this scanning system, where he can go out and over broad scales, like football field scales, he can basically have this LiDAR system spin around, and he gets reflections back from a laser beam, and he can map whole landscapes at like centimeter scales. Okay? And so here's this landscape with this marsh, and this marsh, and this marsh, and this mudflat. And what you see here is a digital interpretation of that landscape made with this laser scanner. And then once you have this map of the landscape in digital space, you can query it for all sorts of things like, elevation at every spot on the map, or volume, or change through time if you take measurements every year, which we've done. And so what we'll do here is we'll just sort of do a little flyby, a little moon landing of this landscape. So again, like this marsh is here, is right here. Let me see that. Yeah. And this mud flat right here is this mud flat right here. And one of these dots here is our boat, and you can like see the T-top on our boat. Everything that's there gets captured in this. So we'll just sort of fly in, and you'll see a reef, and the animation is kind of like a lunar landing. But I like to play it again. I usually like to try to trap it right there. Okay. And so across sort of whole landscapes, what we can see are the mud flat with these pits. And what are these pits created by? Stingrays, right, and crabs. And so we thought, hey, it'd be fun to do a study on stingrays because we can look at how long the pits last and how many there are and how deep they are. We've not done it. But here's an oyster reef, and we basically get hits on every single oyster, right? And so in terms of looking at rugosity or the evolution of these reefs, we have really high-quality data at sort of centimeter scales. And so what we're allowed to do is we're allowed to look at things like, okay, what is the height of a reef or the relief of a reef across its elevation or wherever we want to. And so what you see here is a plot of the aerial exposure. So these are intertidal reefs. So what you're seeing here is they're higher and higher than intertidal. They're out of the water 40% of the day, down to basically being subtidal. They're never out of the water. And it just so happened that John had built his reefs across that gradient without really realizing it. Because these are shown in terms of percent exposure. These are small differences in actual space. Like these are changes in elevation like that, to go from 40% exposure to 30% exposure. And you don't really see that with your eyeball when you're out there. And so there are basically two big patterns. One is for these reefs built on sand flats, where you get this unimodal pattern where if you build them too high to start out with, and let me clarify one thing. All these reefs were built the exact same way. 3 meters by 5 meters by 15 centimeters tall. So what these data are showing is how tall the reefs have grown after that initial construction, which was identical across reefs, and that's an important point. So this reef was built the same as this reef and this reef, but they've grown differently. And so this reef hasn't grown as tall, largely because it was built so high up that it's reached a ceiling fairly quickly, and it can't grow anymore because sea level's there. And these reefs aren't going to grow to be as tall as trees, right? That's not going to happen. So there is a limit. These reefs down here, they're not growing very well for some reason. And, they're oysters, and, they're a marine critter. And growing in the ocean shouldn't be a problem, you might think. And oyster reefs certainly exist subtidally. We know of a lot of subtidal reefs. There are subtidal reefs here in Mobile Bay. But it tends to be these reefs that spend just a certain amount of time out of the water that tend to grow best. And another place you see this exact pattern is in marsh accretion. So this is the pattern of the way marshes accrete. If they're too high and dry, they don't really grow fast enough. They don't accrete. If they're too deep, they get flooded. The plants don't do well. There's a sweet spot at which plants grow really well. There's lots of deposition of sediments and of plant material, and you get maximum accretion rates. That's for those sand flat reefs. Those salt marsh reefs are very, very, very different, right? Like the ecology driving that is completely different. And it has to do, I think, with those little nibblers that feed and other factors about being next to a marsh. But it's not a function of depth. I mean, they're at the same elevation or depth, but they're responding to aerial exposure very differently. And so we did do another experiment looking at this pattern, trying to understand what goes on here. And so our basic shtick was to go build a bunch more reefs. So again, working around Middlemarsh. Middlemarsh is surrounded by these big, huge sand flats, shown here and here and here and here and here. And so we went out and we mapped these sand flats to know the exact elevation. And then we constructed oyster reefs at 4 different depths. And again, we just made boxes of shell, and then natural patterns of settlement and survivorship and growth drove the evolution of these reefs. And the depths that we built these reefs at are at a half meter below mean sea level, or 6/10 of a meter, or 3/4 of a meter, and then 9/10 of a meter. So again, when you leave this room, what I need you to remember is we're talking about that, okay? Like that's the treatment of, that's what we're doing, is we're changing the vertical position like that. And so, these are the depths that we were shooting for. Again, like negative 0.9 meters down to negative a half meter. And these are the depths we got. And so we were pretty good at actually building these reefs at these slight little elevation changes. Now, all the reefs are the same width, same length, same relief to start out with. The only thing that's different is that little bit of difference in exposure time. And again, I choose not to show any bar graphs because I think the pictures tell 1,000 words. So we had reefs that actually did have different footprints, but they had to always have the same relief, I should clarify. So we had large reefs that were sort of larger boxes in the X and Y, not the Z. And we had these small reefs that were just like the Grabowski reefs when they were built. Had these 4 different depths from shallow down to kind of deeper. And, on these shallow reefs, you see tons of oysters after about a year. This is like 1 year. On these deeper reefs, you see more algae, more sponge, and then down to basically nothing, okay? And then here's sort of a low ground profile view. After a year, thousands of oysters per meter squared, thousands of oysters, and then very, very few oysters, and then no oysters. And if you look at the oysters that are there, and you look at the sizes of them, these oysters that are high and dry a lot of the day, they grow really fast. So after a year, they're the size of my thumb. These oysters that are down subtidal, they don't grow well at all. They're like the size of my thumbnail. And this was, to me, the neatest part of the study was, we sampled this like a month after we built them when settlement happens, and then 4 months later, and then a year later. And I'm showing you what happened after a year. Well, at that first sampling event, 2 months later, all the oysters were down here. So if you look at settlement rate, we have an order of magnitude more settlement of oysters here than we do here. But something picks them off, they don't grow well, or there's this post-settlement regulation of their populations. And I won't go into a lot of detail because of time, but basically it's things that you know from the rock intertidal, competition and predation. You see those same things regulating where oysters grow in our system. So they get smothered by algae and bryozoans. They get picked off by crabs and sheep's head. And so this vertical intertidal space is essentially a refuge, okay, for oysters. And just to fill in a little more detail, so I'm not leaving a big piece of the puzzle out, we have subtidal oysters in North Carolina, but not in this area. So how is it that in some places subtidal oysters can exist, but not here? And the deal is just like this is an exposure gradient, which changes the physical stress on a lot of those baddies. So the crabs and the fishes and the boring sponge and the bryozoans, they can't make a living up here. It's too high and dry, but the oysters can. Well, we also have a salinity gradient in North Carolina. We have it here too in Mobile Bay. And so when you move into fresher, more brackish water in North Carolina, things like boring sponge, which is a major problem, it doesn't do well. Drills don't do well in North Carolina when you get fresh water. A lot of the algae that fouls the reef doesn't do well when you get in fresh water. So again, like brackish water is essentially a refuge for oysters from a lot of its enemies, just like this intertidal zone is, just like you know from the rocky intertidal on the west coast or up in Maine. And so, a lot of restoration projects have failed, and we've sort of tried to document them just to get a figure of like how much money is spent, because people built reefs here and not here, because it's a threshold that spans like that, and you're not going to see that with your eyeball, most days. But it's just an amazing threshold that happens. All right, so then the last part, I just want to talk a couple of the services. Yeah, and I may run out of time. So I may get through what the fish do in terms of responding to these oyster reefs, but now this issue of what these reefs are doing relative to carbon. If I was going to be in a meeting with one of y'all later today and you want to ask about carbon, please do. I think there's a neat story there with what reefs do with carbon, but I'll probably just stop before I get there. This guy is a fellow named Matt Kenworthy, who was at Dolphin Island as well. Some of you may recognize Matt. Matt's been at our lab for a while, and he's been leading a number of projects where we're tagging fishes with different approaches and looking at their movement ecology and trying to understand how they use habitats a lot better. And so we've been working right back in this same system for a lot of this work. And, I basically showed pictures, but I will show a little bit of data. So if you look at the density of like crustaceans or other bivalves or worms, anything that a fish might eat, in those oyster reefs that were built either out isolated from other structured habitats or next to a seagrass meadow or next to a salt marsh, there's tons of enhancement of food resources in those mudflat reefs. They're gorgeous. They have lots of oysters. They have lots of critters associated with oysters. All the food's there. And so if I were a fish, man, that's where I'd go, now, right? And I'd try to gobble up all those lovely little worms and bivalves and whatnot. So we got interested in trying to see if fishes were going to respond to this. And we ended up using a system that Sean owns, that he lets borrow, which is a really high-resolution tracking system. And we actually were able to get these tags that transmitted dual ways. So we had a broader scale tracking study throughout the estuaries in our system that Matt is actually working up right now and working on. But we also had the ability to track the fish's movement in this one system at half-meter resolution. So we know if the fish is here, or we know if it's here, and we know that every 5 seconds. And so the basic game, which a lot of y'all probably work with and know well, is you catch a fish and you insert a small transmitter in that fish that sends out a ping, ping, ping. And with this system we had these cabled hydrophones all throughout the system. And if that ping, ping, ping reached 3 of those hydrophones, you can triangulate its position really accurately to that sort of half-meter resolution. And in practical terms, we were catching all these fish and we were releasing them in this fairly small box, and we were turning them loose with these $300 tags, and it was like, bye-bye $300. We'll never see you again. The tide here is it's about 1.25 meters, and at low tide, there's almost no water in the system, and so these fishes leave every low tide. And it was sort of terrifying to put all this money into fish and then turn them loose, knowing they were going to leave and not know if they'd ever come back. To basically a football field, in the ocean. But a lot of them did. We had some fish that came back 30 or 40 different days. We had some fish that came back a day or two, and kind of everything in between. So we ended up with 150,000 interrogations of where a fish is at in this system. And we really want to know, are they using habitat non-randomly, or do they prefer one type of oyster reef over another, or what are they doing? And we tagged red drum and sheep's head. But I'm only going to show data from the red drum. So some places, these data are really impressive to people. Here, y'all do so much of this work yourselves, so I think you've probably seen some of this type of stuff. But what you're going to see is you're going to see these tracks of a fish through time, really high resolution. And in this one case, you're going to see also sort of the video of what the fish might see as it makes this swim through our array. So keep in mind, I've sort of proposed that these mudflat reefs were gorgeous and lots of food. That's where I would go. And then we'll see what the fish do. And you're going to see a fish swim in from right here, and there's going to be a worm that sort of represents where the fish was for a while as it moves around, like one of those millipede games. And it represents every 5 seconds, whenever the fish came in. So here comes this first fish. It enters the system, and it's going to head right to that reef, right where it should, because those reefs are awesome. And it's going to say, see ya. I could care less. And it's going to go right to the seagrass. And this one fish, like if you didn't know where the seagrass was in this system, if you only had the fish track, you would know where the seagrass is at. Because this fish is going to paint this seagrass meadow for like the next 2 hours, okay? And it basically gets to the edge of the seagrass, and it's like a physical barrier. So, it's fine. It's doing something. I can't say that we know exactly what yet, but it's cueing in on something about that. I'm going to stop this one. You can see the top. We have eelgrass. It's pretty short and stubby and weak because the tide's going up and down. So the next video is just to demonstrate to you how cherry-picked the data are, the videos are. So this fish is coming in at about 11 o'clock at night one night. And I'm usually not out there at 11 o'clock at night sampling. But it's going to find this reef, and it's just going to hang there for like 45 minutes. And, you're watching a fish swim. That should just make you happy, right? Because you never get to feed fish swim because they're friggin' invisible when they move. But this fish goes to the grass, and it's like, again, like a barrier. It's like, nope, don't like that. And the fish is actually going to like swim around here in a second. You can actually watch the fish swim. I love watching this fish swim. There it swims. It's a big circle. Like that fish just swam in a circle, right? And so, this reef is the size of a car, a small car. And the fish just spent 45 minutes there. And we're trying to figure out, like, okay, what's the fish doing? Is it feeding? Is it resting? Is it avoiding predators? Is it just, out for a stroll? And so we've done some tethering experiments, look at feeding rates. We've tried to do some video stuff, and it's not gone that great. But so we're building. What we'd really like to do is we'd like to have, red drum in here and crabs in here and, put out clam plots and really manipulate the system and look at movement at multiple trophic levels. But we're not there yet. The last video is my favorite because you're going to see 2 fishes swimming at this time. And the point I'd make here is that the fish spend almost no time at this oyster reef right here. And this oyster reef is clearly like the most important feature in their lives for like this 2-hour period. And it kind of screwed me up for a while because I was like, oh my God, like when we sample with nets, like what does that mean if these, like watch it, these fish spend no time there and it's clearly really important to them. And so if you put out a trap or a net, like what are you seeing? I think there's value in those samples. I'm not saying there's not, but it's messed with my mind for a while. So, all right, you're going to see 2 fish. You're going to see a couple of false detections up here, to be sure. We have fish 1 and fish 2. And they're going to hit that reef, and they're going to go away. And they're going to come back, and they're going to hit that reef, and they're going to go away. And this is at 4 a.m. in the morning. I'm almost never there at 4 a.m. in the morning. And so here they come, and they hit that reef, and they go away. And they're going to come back, and they're going to hit that reef, and they're going to go away. And so again, we would love to know what these fishes are trying to do, and to sort of play games with myself. I say, okay, these fish they're moving faster. We know their speeds, and maybe it was a bunch of red drum. We have 2 of them tagged. It's a bunch of them. Well, if they just hang out above a reef, everything's going to hide, right? And they don't get to eat anything. So maybe when they sort of school up, they have to rush into an area, and that sort of matches what I've seen as a fisherman. And they have to try to grab some straggler. And if they can't find that straggler, the game's up. So you might as well go away. But they want to come back and try to get that straggler again. And so again, we had videos and we had tethers, and everything gets chomped in like 20 seconds. It's a vicious world out there. All right. Yeah, I probably need to try to wrap this up. But so across all the red drum that we tagged, in a very average sense, we tried to ask, okay, well, what habitats are they really queuing into? So on this scale right here, all you really need to know is that anything above 0 represents a preference for a habitat. Anything below 0 represents avoidance of that habitat, or they use it less than they should based upon how available that habitat is. And we see reefs in 4 different landscape contexts: those isolated sand flat or mud flat reefs, reefs near the seagrass meadows, reefs next to the marsh, or there's also this loose fringing shell stuff that you would never pay attention to because it's not really a reef at all. And keep in mind, like, all the food enhancement appears to be right here. And if you look at what the fishes are choosing, like, they distinctly don't choose that. Like, they just don't pay any time, they don't pay any attention, they don't spend any time there. Pretty much the same thing for those seagrass reefs. And sure enough, for those things that fringe the marsh, like, that's where the red drum are spending their time. And they're resting, or they're feeding, or they're doing something there that we don't understand fully. But in terms of the foraging, like, after I saw these data, it's like, okay, I get it. Yeah, like, there's a reason there's all those worms and clams and crabs there. It's a refuge. And if I was a red drum, I wouldn't want to stick my face in consolidated rocky oyster reef, 4,000 per meter squared. I'd want to go to that loose, soft stuff and poke around and turn over stuff and try to grab a mud crab out of that. But that's a very simplified view. We can also look at the patterns of every individual red drum. And we actually, somehow we got connected with a group that was publishing a special session on individualization behaviors. And so what you're seeing here is you're seeing lots of different fish, individual fish, and how they use habitats. So the blue is one type of oyster reef, the green is another. And the point here is that it runs the whole gamut. So some fish within this population, they're specialists on the one type of reef, and other fish, they specialize on a very different type of environment, right? So we could talk about the average red drum. That exists if we average all the data. And you could say, well, the average red drum uses about half and half. And that's very true, because maybe every red drum uses half and half, or half the red drum use all of one, and half the red drum use all the other. And so we've been digging into that issue a fair bit now. And again, that complicates how I think fishery production is linked to habitat availability when you see this pattern relative to, like, every fish does the same thing. And to sort of tie back into that one concept about, as you scale up habitat area, what do fishes do? We've used a number of our sort of tracking studies to look at that issue. So what you see here is you see patch size of a habitat. So this is a small patch. These are really big patches down here. And this is that same sort of data. They show a preference for a habitat. They show avoidance of that habitat. And when the patches are small, the fish seem to have the ability to make a decision. They can choose to go to it or avoid it, like they're doing something. But as the patches get much bigger and bigger and bigger, it's almost like the fish's, their ability to choose just goes away. And they're going to use that habitat about in proportion to how available it is, which is what happens when you see the data along the zero. Which, again, complicates how we understand how habitat links to fish production. All right, so I'm going to skip the stuff about carbon, but if we were to talk later, feel free to come chat with me about it. There's some neat stuff there. But to summarize, I kind of want to try this. This may crash and burn. But this takes several pieces of data, not all of which are mine by any means. But it gets to this issue again, how does landscape matter? So what you're going to see here is you're going to see 3 different oyster reef landscapes, these intertidal reefs out on sand flats, subtidal reefs that are also out on sand flats. We do have a few subtidal reefs we work with in this system. And then those reefs that are up against the salt marsh. And then we just say, okay, let's talk about oyster density. Where do you see oyster density being high? Like, where is it low? There's a big gradient there. Well, what do we know from our stuff or other people's stuff, like nitrogen removal, about which type of reef performs the best services? And it's very different. You might want a subtidal reef if you want harvest or if you want provision of fish habitat. But you wouldn't want that type of reef if you wanted maybe denitrification or water filtration. I didn't get a chance to get to it, but in terms of this carbon burial thing, these 2 types of reefs and these landscapes over here, either subtidal or fringing salt marsh, they're providing a service. They do actually capture carbon in a way that's useful for us. It turns out these intertidal oestuaries, they actually perform a disservice. They're venting CO2 to the atmosphere. So, you know, how you do your restoration is I think, impacted by this. Like, what service do you want to key in on? Do you want them all? Do you want to build reefs in all three landscapes, or do you really want to focus on fish production or shoreline stabilization or water quality? I think these are non-trivial things, and it's a good example of, I think, how landscape can really inform how we do really applied stuff like restoration work. All right, so with that, I'll say thank you, and I guess take any questions.